All right, let's dive right into this. Welcome to today's Explainer, where we are going to completely master one of the most classic yet, let's be honest, frequently fumbled procedures in the chemistry lab. We're talking about the thermodynamics practical, specifically calculating the enthalpy of neutralization. If you've ever wondered how to flawlessly execute that quirky little polystyrene cup experiment, crunch your post-lab numbers without breaking a sweat, and entirely dodge those sneaky little traps examiners just love to set for you, well, you are absolutely in the right place. Consider this your ultimate guide. So here is the core mystery we're unpacking today. Picture this. You take two totally clear room temperature liquids. You pour them together and suddenly, no joke, the cup in your hand feels like a hot cup of coffee. The temperature just spikes. But why? Well, it's because chemical bonds are actively breaking and forming. That beautiful, invisible reshuffling of atoms is literally releasing raw energy into the water. Today, we aren't just going to sit back and watch it get hot. We are going to capture that heat, measure it, and calculate the exact enthalpy change. To get there, here's our clear roadmap for the explainer. 1. Safety first. 2. The calorimeter setup. 3. Crunching the numbers. And 4. Common exam traps. Okay, Section 1. Safety first. Chemical hazards. Let's break down our two main players today, hydrochloric acid and sodium hydroxide. Now, we are typically using standard 1.00 mole per decimeter cubed concentrations here. Make no mistake, that is strong enough to do some real damage. Hydrochloric acid is highly corrosive and emits these irritant fumes. Sodium hydroxide, also incredibly corrosive and can cause severe skin and eye burns. So before you even think about touching a beaker, your safety goggles are securely on your face, your gloves are on, and you are handling these solutions with deliberate, focused care. Moving right along to Section 2, the calorimeter setup. Executing the experiment. You know, you really don't need a $1 million lab to measure thermodynamics. You just need the right scientific principles. In fact, our most crucial piece of apparatus is actually a very high-tech polystyrene cup. Seriously. Why? Because it's a fantastic thermal insulator, which minimizes the heat loss to the room. But as you know, polystyrene is super light and tips over easily, so we nestle it securely inside a glass beaker for structural support. You'll also need a thermometer reading to the nearest 0.5 degrees, a stirring rod, and, this is absolutely crucial, 2 separate 50 cubic centimeter measuring cylinders. You never, ever want to accidentally mix your acid and alkali in the measuring stage. Okay, imagine you're standing at the lab bench right now. Step 1. You measure exactly 50 cubic centimeters of hydrochloric acid into your cup. You'll let it sit for a moment, then record its initial temperature. Step 2. In your other cylinder, measure 50 cubic centimeters of sodium hydroxide and record its initial temperature. Step 3. The moment of truth. You quickly pour the sodium hydroxide directly into the acid. Step 4. You immediately start stirring gently and continuously, watching that thermometer like a hawk to capture the absolute highest temperature it reaches. I really want to highlight this specific instruction because your physical action right here is literally the difference between passing and failing this practical. Think about it. If you don't stir, the heat just pools in little pockets and your thermometer reads incorrectly. But if you wait too long to read the thermometer, the heat escapes into the air and your data is completely ruined. You have to stir constantly and lock in that maximum peak temperature. All right, Section 3, crunching the numbers, from data to enthalpy. Transforming your raw thermometer readings into a final enthalpy value is basically a 3-part mathematical journey. First up, we find the exact temperature change, which we call delta T. We use that to calculate the raw heat energy released in joules, which we represent with a Q. And finally, we scale that energy to 1 mole of water to find our standard enthalpy change, or delta H. Let's walk through a practice scenario. Step 1 is finding your true temperature change. Let's say in our practice data, your acid was 21.5 degrees and your alkali was 22.0. Their mean initial temperature is 21.75 degrees. If your reaction hit a maximum of 29.0 degrees, you just subtract the initial mean from the max. So in this case, 29.0 minus 21.75 gives us a delta T of 7.25 degrees Celsius. Now, take a really good look at this specific number, 4.18. This is the specific heat capacity of water. Simply put, it means it takes exactly 4.18 joules of energy to heat 1 gram of water by 1 degree Celsius. Lock this into your brain, because this is the critical mathematical key that unlocks the next step of our equation. Let's use that key in step 2, calculating Q, our heat energy. The formula is Q equals mc delta T. That's mass times specific heat capacity times temperature change. For mass in this scenario, we assume the density of our solution is the exact same as water, 1 gram per cubic centimeter. Since we mix 50 and 50, our total mass is 100.0 grams. So our equation is 100 multiplied by our constant 4.18 multiplied by our temperature change of 7.25. Let that math sink in for a second. That calculation gives us a result of 3,031 joules of raw energy released straight into that cup. For step 3, we make our final mathematical leap. You see, the scientific community doesn't just want raw joules. They want to know the standard enthalpy change per mole of water formed. Since we used 50 cubic centimeters of a 1.00 mole per decimeter cube solution, we calculate that we formed 0.0500 moles of water. To find our standard enthalpy, we simply take our 3,031 joules and divide it by our 0.05 moles. Which brings us to this crucial final value, negative 60.6 kilojoules per mole. We converted those joules to kilojoules, but notice that negative sign. That is incredibly important. But wait a second. If the theoretical textbook value for a strong acid and base is usually around negative 57.1, why does our math look like this? Why do experiments always seem to fall short in the real world? Let's decode that. This brings us perfectly to section 4. Common exam traps and error analysis. So, the textbook theoretical value for neutralizing a strong acid with a strong base is exactly negative 57.1 kilojoules per mole. But in the messy reality of the lab, your experimental value will almost always be less exothermic. That means a smaller magnitude of heat is successfully recorded. Why do you think that heat seemingly vanishes into thin air? Well, spoiler alert, it didn't vanish. Physics simply took its toll. Sure, your polystyrene cup is a good insulator, but it's far from perfect. Heat is constantly escaping through the walls. Furthermore, our formula, Q equals mc delta T, mathematically assumes all the energy went directly into heating the water. But in reality, some of that energy was stolen to heat the physical glass of the thermometer and the cup itself. Plus, heat is escaping through the evaporation of water right out of the open top of your cup. And this brilliantly illustrates the single biggest exam trap students fall into. You watch the thermometer go up from 21 degrees to 29 degrees, so you automatically write down a positive enthalpy value. No! A temperature increase means the reaction released heat to the surroundings. It is an exothermic reaction. Therefore, the enthalpy change, delta H, must always be negative. If you forget that tiny little dash, you lose the marks. It's that simple. And here is the second massive trap. The total mass trap. When plugging numbers into Q equals mc delta T, students routinely put in 50 for the mass, just because they're staring at the 50 cubic centimeters of acid. But remember, you mix the two together. The thermometer is measuring the temperature of the entire combined pool of liquid. 50 plus 50 equals 100 grams. Always use the total volume. We've covered a lot of ground today, from lab safety all the way to the final calculation. So I want to leave you with a provocative thought to really test your inner chemist. We know our simple polystyrene cup leaks heat, which skews our data. If you had an absolutely unlimited budget, how would you redesign this calorimeter to capture every single joule of energy? Think about adding sealed lids, vacuums, digital temperature loggers. Understanding the flaws in our basic apparatus is the very first step to truly mastering experimental chemistry. Keep thinking critically about your setups, and you are going to completely ace that practical.